Start with the meter, not the mood. On wind-scrubbed headlands and remote islands, flasks fill with clean marine air. Back in the lab, analysts compare the O2-N2 ratio against mid-198's reference tanks with per meg precision. Changes of a few dozen molecules per million. The line slopes down. About 19 per meg per year. Since the late 198s, that's roughly 0.1% of the atmosphere's oxygen. Too small to feel in your lungs at sea level. Big enough to matter where systems run on margins. What's spending it? Two culprits, one loud, one quiet. Combustion first. Burn carbon and hydrogen, and you bind oxygen into CO2 and H2O. The planetary ledger is explicit. Fossil fuel use pulls O2 down, molecule for molecule with carbon oxidized. The quiet thief is heat. Warmer surface waters hold less dissolved oxygen. Solubility drops as temperature rises. Stratification pins what oxygen remains in thin sunlit layers, starving depths. Argo floats don't editorialize. They profile expanding oxygen minimum zones. Coastal sensors catch seasonal dead zones growing where nutrients and heat stack the deck. Now, a straight clarification. Global air still holds about 21% oxygen by volume. That's well above hypoxia thresholds at sea level. So why care? Because civilization runs on edges. Flammability envelopes tighten as oxygen drops or as CO2 and water vapor dilute air. A flame that used to catch cleanly in cooler, drier conditions now starts reluctantly, soots more, quits sooner. Wildland fires flip towards smolder in warm, smoky boundary layers. Smolder is harder to kill and dirtier to breathe. Firefighters feel that shift long before city monitors do. Engines notice too. Turbines and pistons don't care about percent. They care about partial pressure. At altitude, air thins. Designers expect that. Add subtle background O2 decline and moisture, warmer intake air, and relight envelopes narrow. Ignition kernels cool faster, lean blowout comes earlier. Certification standards and pilot training account for the worst corners, but corners move. Maintenance logs quietly record sluggish relight, exactly the kind of micro signal that tells you margins have narrowed. Hemoglobin's curve is steep across the middle. Small changes in alveolar oxygen, CO2, and temperature nudge saturation more than intuition expects. Bodies are instruments tuned to gradients. In a crowded, warm, poorly ventilated room, elevated CO2 and heat shift the curve. Effective oxygen delivery dips, even if air composition is nominal. Athletes, NICU clinicians, and high-altitude workers manage this every day with pacing, titration, acclimatization. Cities meet it during heat waves and smoke. ERs see more cardiac and respiratory stress, not because the global 21% vanished, but because local delivery faltered. Signal versus noise matters. The Scripps O2 program's trend is robust, cross-checked against CO2 inventories, and mirrored by independent stations. A 12-year continuous series from the UK finds about -24 per meg per year for O2, consistent with the global picture. NOAA-backed analyses outline upper bounds on future O2 loss that still don't threaten direct respiration at sea level. But they don't promise comfort at edges. Aviation tolerances, flammability limits, coastal hypoxia, human performance in heat and stale air. The ocean's role is the hinge. Warming reduces solubility. Circulation controls delivery. Biology spends what physics allows. There's a human blind spot that makes slow danger easy to miss. We calibrate to now. You won't walk outside and say, O2 is 0.1% lower than when I was born. But the systems that turn air into work do report it, in sootier starts, in narrower relight maps, in fish pinned into thinning habitable bands. Buildings hide it with smart fans, jet controls mask it with software, hospitals buffer it with oxygen plants. Resilience is real. It also acts like camouflage. So where are the thresholds? For many hydrocarbons, the limiting oxygen concentration sits in the low teens at standard pressure, but temperature, pressure, humidity, and diluents move it. In aviation, relight requirements are codified. Aircraft must prove flame stability across worst-case altitude, speed, and temperature. Warmer, wetter backgrounds thin the cushion. At sea, oxygen minimum zones expand laterally and upward, nudging fisheries toward coasts and storms. On land, cognitive performance dips in poorly ventilated schools track CO2 and heat, stand-ins for oxygen delivery stress. None of this is apocalypse. It's a baseline shift with consequences. The fix list isn't exotic. Cut combustion so the oxygen bill shrinks. Cool and mix waters so the ocean can share its oxygen. Design engines, buildings, and protocols for thinner margins. Make oxygen supply in hospitals and cockpits boringly reliable. The meter keeps falling, molecule by molecule. The right response is to pay attention where edges matter. The match, the turbine, the ward, and move the edges back. Fire's secret contract, the oxygen combustion economy. Civilization runs on tamed flames. Boilers, turbines, furnaces, engines, kilns. But fire isn't a switch. It's a contract with oxygen that has clauses and penalties. Break the terms. Drop the oxygen fraction, add diluents like CO2 and water vapor, lower intake temperature or pressure, and the flame doesn't rage. It hesitates, soots, or quits. Ignition is clause 1. A spark must seed a radical pool. Chain branching reactions involving H, O, and O's that outruns heat loss. That balance defines the limiting oxygen concentration, the floor below which a flame won't propagate for a given fuel, pressure, and temperature. In clean, dry air at sea level, many hydrocarbon air systems burn down into the low teens oxygen by volume. Add humidity, smoke particles, or CO2, and that nose shifts upward. Minimum ignition energy rises. Lean blowout arrives earlier. Laminar flame speed falls, and turbulent flames, our workhorse, lose their cushion. Clause 2 is stability. Burner designers fight a tug of war. Too slow a flame, and it lifts off and blows out. Too fast relative to flow, and it flashes back, damaging hardware. Lower effective oxygen trims, laminar flame speed, and widens the range of flow conditions that end in liftoff. Industrial burners compensate with swirlers to anchor the flame, pilot fuels to ensure hot kernels, staged air to keep radicals fed. Those work until ambient conditions nudge every margin the wrong way. Warmer, moister intake air, a tick leaner oxidant, slightly cooler preheat, and a start that used to be routine becomes temperamental. Clause 3 is completeness. Slow radical chemistry means more incomplete combustion. Carbon monoxide, unburned hydrocarbons, aldehydes, soot. You didn't just lose heat output, you gained pollutants and fouling. Soot loads heat exchangers and turbine vanes, pushing maintenance forward. Co-trip monitors that never blinked now catch tired starts. Plants respond by richening mixtures, upping preheat, or lengthening igniter duty cycles. Each fix a quiet admission that the contract term shifted. Industry knows these terms in reverse because it uses them for safety. Inerting systems, flood tanks, and vessels with nitrogen to push headspace below a tested limiting oxygen concentration. Jetliners carry on board inert gas generation to keep fuel tank ullage lean enough that a spark becomes harmless. Those lock values depend on pressure and temperature. Winter ramps aren't summer ramps, takeoff isn't cruise, and margins are sized to worst cases. A background slide in oxygen availability or added diluents from hotter, wetter air doesn't nullify the design. It narrows the cushion. Engines write a stricter addendum. A piston engine must carry a turbulent flame across a cylinder in milliseconds. Slower flame speeds from lower effective oxygen or higher diluents shrink the stable map. More misfires at lean, more knock risk at rich. Designers fight back with boost, tumble, multi-spark, and stratified charge. But the fundamentals remain. Partial pressure pays the bill. In gas turbines, combustors must light and stay lit across altitude, speed, and temperature. Certification demands relight across cold, thin air. Operators practice for flameouts. Warmer, moister ambient, and a barely leaner background, O2 tilt the odds. Ignition kernels run cooler. Relight times lengthen. Maintenance notes hesitant light at conditions that never used to raise eyebrows. Wildfire carries the same contract into the open. Oxygen-rich air lowers ignition thresholds. Oxygen-lean or diluent-heavy air nudges behavior towards smolder. Smolder creeps, resists water, and pumps particulates. Crews hate it because it steals clean edges and lungs. The charcoal record is the long-term ledger. Fires proliferate when oxygen is high and retreat when it's low. Today's shift is subtle. warmer, moister, smokier boundary layers in some regimes, plus micro drops in effective oxidant mean more stubborn starts in certain fuels and conditions, and nastier smolder once they go. Human spaces aren't exempt. Kitchens and boilers feel lazy flames on humid, high ozone afternoons. Pre-mixed burners lift and spit. Crematoria and kilns tweak air fuel to keep color and phase on spec when intake air carries more water. Hospitals test backup generators under load during heat waves because warm, dilute intake air makes first-turn success less guaranteed. Each adaptation is small. Together, they map the contract. None of this claims ambient oxygen has fallen anywhere near levels that threaten breathing at sea level. Measurements from programs like Scripps put the decline near 19 per meg per year, about 0.1% over the modern record. But combustion lives on thresholds, not averages. The same fractional slide, plus heat and humidity, raises minimum ignition energy, lowers flame speed, and narrows stability windows. In systems built to edges, turbines at altitude, emergency starts, inerting set points trimmed to weight and cost, that matters. The path forward isn't mystical. Trim the oxygen bill by retiring unnecessary flames. Electrify end uses where practical. Where combustion stays, design for thinner margins, better igniters, flexible staging, real-time controls that sense humidity and oxygen, and adjust. Keep inerting honest to tested LOCs across temperatures and pressures. Train for relight and verify under the new corners, not the old ones. The contract hasn't been canceled, it's just charging late fees. Thin air, aviation, engines, and edge of failure physics. Up where oxygen is thin, machines and people live by numbers, not hope. Engines don't see 21%. They see partial pressure, temperature, humidity, and whether a flame kernel can outrun cooling inside a rushing tube of air. That's the edge of failure world, and tiny drifts show up early. A jet engine is a choreography of margins. Compressors squeeze thin air, injectors atomize fuel. The combustor lights and must stay lit while a turbine skims energy to keep the cycle spinning. At sea level, there's padding. At 35,000 feet, oxygen per gulp is a fraction of home. That's expected and certified. Relight envelopes are proven across altitude, speed, and temperature. But add warmer, moister intake air and a subtle background O2 decline, and those envelopes narrow. Minimum ignition energy rises. Kernels cool quicker. Lean blowout edges closer. The checklists haven't changed, the corners have. Sensors don't report vibes, they report partial pressures and flows. Military and commercial jets with onboard oxygen generation systems blend and concentrate O2 to keep pilots within safe saturation ranges despite cabin altitude. NASA's pilot breathing assessments map how mask pressure, O2 fraction, and CO2 washout interact under workload. The lesson is blunt. Physiology sits on the same MAF as combustors. A small shift in alveolar oxygen, or CO2, changes performance on steep parts of the hemoglobin curve. Long-haul crews feel it as fatigue, a miskeyed waypoint, a sluggish fix caught by CRM before it becomes a story. Compressors hate surprises. Swallow a gust, a sheet of rain, or a distorted inflow in clear air turbulence, and stall margins shrink. Combine that with thin air, higher humidity, and slightly reduced oxidant availability, and a transient that once recovered on a single spark now takes two. Certification demands relight under icy thin conditions. The physics is rehearsed. But real weather is trending warmer, wetter in many routes, and the safety cushion is thinner there. Maintenance logs capture it best. Hesitant light, longer spool, notes that read boring and mean everything. Piston engines live closer to the flame. A turbulent front must cross a cylinder in milliseconds. Lower effective oxygen and higher diluents slow flame speed and tighten the stable map. Misfires lean side, knock rich side, pilots lean mixtures by EGT and sound. On hot, humid days, the same setting runs rough sooner. Smoke season adds CO and particulates, displacing clean intake and cooling kernels. The fix is simple. Adjust earlier, accept performance hits, but the pattern is new enough to be noticed. Cabins are engineered kindness. Pressurization holds the cabin at a fraction of outside altitude to prevent hypoxia and decompression sickness. None of that fails because global O2 has slipped by 1% since the late 198. Oxygen masks drop if needed, and systems are sized to cover escape profiles. But effective delivery still depends on partial pressure, CO2, and temperature. Warm cabins with elevated CO2 from packed flights nudge physiology down the same slope as a combustor kernel. Harder to start, easier to quit. Training and procedures absorb the drift. It shows up as hydration strategies, rest cycles, and subtle changes in how crews manage workload on red eyes. Fuel chemistry adds its own fine print. Sustainable aviation fuels must match energy density and ignition behavior across conditions. Standards demand that relight and stability meet spec at altitude and low pressure. Warmer, wetter backgrounds don't rewrite those specs. They shave the margin. A blend that lights crisply in a cold, dry test might hesitate on a tropical night at cruise. That's why airworthiness standards build in worst-case corners, and why test matrices keep expanding to reflect the air we actually fly through. Regulations quietly encode the stakes. Transport standards require fire protection across systems and reliable ignition behavior under defined extremes. The point isn't drama. It's designing so that tiny atmospheric drifts never become incidents. Still, the edge isn't abstract. An auxiliary power unit that balks after a warm soak on the ramp, a crossbleed start that needs a second attempt, a descent through smoke that leaves passengers lightheaded. Each is a breadcrumb pointing to the same constraint. Less effective oxidant, more often. Meanwhile, oceanic routes see the knock-on effect from below. Warming, stratified waters ventilate less oxygen, compressing marine life into thinner bands. Jets that skirt those bands fly in air masses shaped by the same heat. Clear air turbulence patterns shift with changing gradients. Distorted inflow events have subtly different statistics. The engines still start, the flights still land, but the system is earning its safety the hard way. Clarity matters. The Scripps O2 trend, around 19 per meg per year decline in O2N2, doesn't endanger breathing at sea, level. Aviation authorities don't flag ambient O2 as a causal factor in accidents. What it does, alongside heat and humidity, is trim margins that were never lavish. That's why operators test relight in hotter, wetter regimes, why mask systems are audited against real workloads, why maintenance squawks about lazy lights get read twice. The fixes aren't exotic. Update relight maps with live humidity and temperature inputs. Validate sustainable fuel ignition behavior at the real corners. Keep pilot oxygen systems transparent and conservative. Practice flameout drills in the new atmospheres, not the old ones. The sky still carries us. It's just charging interest on every assumption. Bios redline bodies, brains, and the oxygen tax. Start with stakes you can feel. Your brain is 2% of your mass and takes around 20% of your oxygen. Miss a sliver in delivery, and it doesn't scream. It blurs. Names pause, choices slow. In hypobaric chamber studies and long-haul flights, healthy adults lose attention and working memory with modest dips in alveolar oxygen, especially when CO2 and heat rise together. Hemoglobin's S-curve explains it. The middle is steep. Small shifts in partial pressure, temperature, or CO2 move saturation more than intuition allows. Action. Researchers walk volunteers up mountains or simulate altitude. EEGs show changed power spectra. Reaction times lengthen. Sleep fragments with apneas and arousals. At cabin altitudes of 6,000 to 8,000 feet, many sit with blood oxygen saturation in the low 90s without noticing. Add dehydration, circadian slump, or smoke, and the baseline phrase. VO2 max declines predictably with altitude. Athletes train around it, workers pace around it. Meanwhile, urban microclimates recreate a softer version at sea level. Heat, humidity, elevated indoor CO2, and pollution dilute effective oxygen and shove physiology down the same slope. Micro-stories make it real. A nurse on a smoke day hustles between rooms. Patients need higher oxygen flows for the same saturations. Charting lags, her watch logs the day's highest heart rate. A teacher cracks a window in a warm classroom. CO2 creeps past 1,500 ppm. Kids get foggy, not defiant. In a high-rise gym after a heat wave, the same workout feels heavier. Sleep that night is restless. Nothing catastrophic, everything nudged. Mechanism matters. Oxygen transport is a gradient game. Ambient air to alveoli, alveoli to blood, blood to mitochondria, raise CO2 and temperature, and the dissociation curve shifts right, the Bohr effect, making hemoglobin unload oxygen more readily in tissues but bind less in lungs at a given partial pressure. That helps in muscle, hurts in marginal lungs. Add smoke's carbon monoxide, which binds hemoglobin 200 times more tightly than oxygen, and capacity shrinks. Wildfire seasons stitch that chemistry into daily life. ERs see more cardiac and respiratory events, not because oxygen vanished, but because delivery faltered. Infants and elders live closer to the edge. Neonates and NICUs rely on tight oxygen windows. Too little steals development, too much scars eyes and lungs.